Lesson 2.6, Representing Relationships. As we've discussed, a relation is any relationship between sets of information or numbers. They can be represented as a table, a graph, a set of ordered pairs, an equation, or a mapping. And data from each of these representations can be interpreted. Graphs are used to give us a pictorial representation, so a picture to look at. So the reason we have this is because if you see a picture, you can quickly assess what's happening without having to do a lot of calculations or comparisons. So representing relations with graphs, I have some graphs that I'll show you, and we're going to interpret some information. We're going to find out what the independent variable is, what the dependent variable is. We're going to identify the domain, the range, what the meaning of the changes in the graph are, and any information that can be obtained from the graph. Okay, so let's start. Here we have a graph representing a Saturday bike ride. So let's figure out what is the independent variable. This is the thing that there's really no control over. It'll change on its own, or we can choose it. And in this graph, the independent variable is time. Next, we have the dependent variable. And in our graph, we've got time versus speed or velocity. So as our time is changing, so is our speed. So our dependent variable is going to be the speed. The domain, that's the set of our independent variable, or our x's. And if we look at that, we have 0 through 8. So our domain is going to be x is greater than 0, because we can see that the graph would continue. Our range is our y's. Now this is not giving us exact speeds, so why don't I go ahead and assign those a number. We'll just say 10 meters. Oh, that's really fast, 10 meters per second. We'll say 1 meter per second and 2 meters per second, just to assign it some numbers. And so our range would be y, and y is, we go between 0 when we're stopped, and it looks like our maximum speed here would be 2 if that was the value. Okay, the meaning of the changes in the graph. So as you can see, we're moving up, then we're flat, then we're moving up again, and then we're flat. While we're moving up, our speed is changing, we're accelerating. And when we're flat, we're staying at a constant speed. So we accelerate here, and we're at a constant speed here and here. So we've marked those on our graph. And then we have the information that can be obtained from the graph. Well, we're going to be making some guesses or suppositions. Okay, someone's going on a Saturday bike ride. They start and they are riding fast for 1 minute to get up to speed. Then they maintain a constant speed. Perhaps they're going uphill, or perhaps they're just coasting along. Then they decide to accelerate some more, and then maintain a constant speed for the rest of this ride. Okay, our next graph we have is of PC game sales from 1994 to 2007. Our independent variable is the year. These years are going to exist whether we have anything to do with it or not. 1994 happened, 2001 happened. So they are independent, our year. Time is always going to be your independent variable because we cannot control it. Our dependent variable is going to be the amount of sales, because the amount of sales depend on what year we're selecting. Our domain is going to be 1994 through 2007. Our range, it looks like our lowest price is down here under 1,000. So if this is 500 and this is 1,000, that's about 750. So maybe 900. So our range will be between, say, 900 to almost 2,500. So we'll say 2,400. Again, this is a rough guess. Okay, the meaning of the changes in the graph. As we're coming along throughout this portion of the graph to here, so 1994 to 1997, this is increasing sales. Then we have a period of decrease. Then we increase again. And then we decrease. Then we have a brief increase. And then the rest of the graph is decreasing. Okay. And the information that can be obtained from the graph. Well, between 1994 and 1997, PC game sales were increasing. This was probably due to the fact that during this time period there was a rise in personal computers. 97 and 98 saw a slight decrease in sales for whatever reason. Then we had 98 to 99, we had a small increase, again for whatever reason. Looks like from 99 to 2000, there was a large decrease. That's probably because people were concerned about Y2K and they thought the computers were all going to fail anyway, so why buy any video games? Then from 2000 to 2001, you have a small increase, maybe because they realized that the computers weren't failing and so woohoo, we can buy games again. And then from 2002 on, it continues to decrease. And I believe that this would be due to the rise in popularity of gaming consoles versus PC games. Okay, we can represent relations in additional ways. Each of these graphs could have been represented in another way. We could have represented them as sets of ordered pairs. So if we call this one graph 1 and this one graph 2, graph 1 could be represented as the set 0, 0. That's this point right here. The set 1, well, we're going to call that 1. And then we also have 2, 1, and 3, 1. And then 4 was increasing. We're about here, so we'll call that maybe 1.5. And then we have 5, 2, 6, 2, 7, 2, and 8, 2. Our second graph, we're going to have to make some guesses about the actual dollar figures. Got 1, 2, 3, 4, so that 100, 200, 300, 400, 500. So each of these is 100. In 1994, we're at about 1,300, so we could say 94, 1,300. And then in 95, 95, we're at 16, 17, 18, 1,900. In 96, we're about 2,200. In 97, we're not much more, maybe 2,250. 98, gone down back to 2,200. And we could have continued, but I'm going to go ahead and stop there. But as you can see, each of these graphs could be represented as a set of ordered pairs. You just find the coordinates on the graph, and those are your ordered pairs. Many relations can also be represented with equations. Now, the graphs that we showed a moment ago could be presented with complex equations, but because they're not linear and they don't follow an exact pattern of a parabola or some other graphs that we're really familiar with, they would be very complex equations. However, we can write the equations for graphs of straight lines very easily. So we have this graph represents the total cost of apples purchased by the pound. As the number of pounds increases, so does the total cost, and we can use this to create an equation for the price of apples. What we do is we find our slope, so I'll pick one point and another point, and we go up 1, 2, we'll just say that's 2 over 1. So our slope is 2 over 1. Now if we use our equation y equals mx plus b, b is our y-intercept. We're hitting the y-axis right here at 0, so b will be equal to 0 and m will be equal to 2. So I can write in my graph 2x plus 0, and then I can simplify that to be 2x. So y is equal to 2x would give us our equation for the price of apples. Here's another graph representing the acceleration of a car leaving a stoplight, and we can write an equation to represent this as well. Time is our x value, velocity is our y value. At 2 seconds, we're about 15. And then let's try to find another good point. Let's see, 6 would be here, 4 would be here, 8 would be here, and then if I line up, that does line up with the 20. So I'm going up 5 over 2. So my slope is going to be 5 over 2. My intercept, my y-intercept, where I put the y, is right here, and I'm going to say that that's about 12. And so my equation for this graph is going to be 5 halves x plus 12.